Today we are going to prove an interesting result from analysis and namely known as Archimedean property. So I am going to prove Archimedean property. What does it states? It says if you take x and y be any two real numbers and x is positive and x is less than y, then there always exists some n belongs to n such that nx is always greater than y. Nx is always greater than y. This is known as Archimedean property. So given any two real numbers for all x and y with this condition, x positive and x is less than y, we can always find at least one n. And this is very natural in a sense. If I take say a real line and suppose if I consider two real numbers, say x and say y, like this, where x is less than y, then if you keep on adding x with itself, after some stage that value, that resultant value will definitely cross y. It will be larger than y. Means x plus x, for example, you will get 2x. X plus x plus x, you will get 3x. And you may get x plus x plus x, that is 4x, somewhere here. So in this case, we have 4x is greater than y. So this 4 is the value of n. This is the simple logic behind Archimedean property. But let us prove this result mathematically. So I am going to prove this by contradiction. Suppose this result is not true. Suppose if possible, the result is not true. The above result or Archimedean property is not true. What does this mean? This means there exist some real numbers, say x and y in R, with x less than y, x positive, but this nx greater than y condition does not hold. Means nx is not greater than y for any value of n, belongs to n. What does this mean? This means nx is less than or equal to y for every n belongs to n. This I am calling result number 1. So from this, what I am going to do next is I will define a new set. And call it S, like this. So define a set capital S is equal to set of all numbers of the form nx. So I am collecting all the nx for different values of n. Means the set S contains say x, 2x, like this, x, 2x, 3x, and so on. So our set S is this. Note that here x is a real number, and therefore it is also in S, and therefore S is non-empty. So first of all, it is clear that S is not empty, and since x to x all are real numbers, this S is a subset of R. So we have these two properties of the set S. Also we can say by result 1, also by result number 1, the number y, you can see here, this y is always bigger than all the numbers in the set S. So y is an upper bound of the set S. So I can say y is an upper bound of the set S. Is an upper bound of the set S. So we have three properties of the set S. It is non-empty, it is subset of R, and it is bounded above. So this means the set S is, because whenever a set has at least one upper bound, we call it a bounded above set. So S is bounded above by Y. S is bounded above by Y. So these three things, S is non-empty, S is non-empty, S is subset of R, and it is bounded above, tells by completeness of R. We know what is the completeness property. R is a complete field. So means every subset of R which is non-empty, bounded above, has always least upper bound in R. So I can say, since R is a complete order field, so there exists a least upper bound of S in R. So I can say there exists a number alpha in R such that this number is the least upper bound of S. So we have got a number alpha which is the least upper bound of S. We also have the number x, and we know x is positive. This x, which is also in S, is positive. So I can say as x is positive, what is this? Since x is positive, alpha minus x is less than alpha. If you remove some positive quantity from a given number, you get a smaller number. So alpha minus x is less than alpha. But what is alpha? Alpha is a least upper bound of S. But alpha is least upper bound of S. And here we are saying that alpha minus x is less than alpha. So this alpha minus x cannot be an upper bound. It cannot be an upper bound of the set S. It cannot be an upper bound of the set S, because it is the least upper bound, it is the smallest upper bound. So anything less than that cannot be an upper bound. So alpha minus x cannot be an upper bound of the set S. What does this mean? This alpha minus x is not an upper bound of the set X, which contains these elements x, 2x, 3x, like this. So there is something in this set which is bigger than alpha minus x. So there exists some element in X. What are the elements of S? Elements of S are of this form. So I can say there is some natural number m such that a number of the form mx is greater than alpha minus x, and that gives us mx plus x greater than alpha, which means m plus 1 into x is greater than alpha. M plus 1 into x is greater than alpha. But what is m plus 1 into x? M plus 1 into x is an element of the set S, because S contains all multiples of x. M is a natural number, so m plus 1 is also a natural number. So m plus 1 into x is an element of the set S. So what we have proved is there is some element in S, and that element m plus 1 into x, this element is greater than alpha. It is greater than alpha. This element of S is greater than alpha. So that is not possible because alpha is the least upper bound of the set S. So all elements in the set S must be less than or equal to alpha. But we are proving here there is something which is greater than alpha. So therefore our supposition must be wrong. So we are getting a contradiction here. So our supposition must be wrong. This is a contradiction. We are getting a contradiction because of our wrong assumption. So therefore our assumption is wrong. Hence Archimedean property is proved, or we can say Archimedean property holds true. This holds true. Thank you.